Hi everyone. Today we're going to be talking through position, velocity, and acceleration, which is obviously a topic we've worked with before, but we're going to be approaching a bit differently. When we've worked with these types of problems in the past, we've typically been given the position function, and we've had to use derivatives to find out information about the velocity and acceleration. However, at this point, most of the problems that we're going to look at around position, velocity, and acceleration, for most of these problems now, we're going to be given information either in the form of a table, a graph, or an equation, but we're going to be given that information about the velocity function. So our starting point for these problems is going to be a little different. Again, it's not just going to be dealing with position, but rather starting with velocity and then getting to some of these other functions using integrals and derivatives. So as we talk through these terms that we've obviously worked with before, we're really going to be defining how we find them if we're starting from the velocity function. So the first term we have here is displacement, right, which we know is just the difference between where an object starts and where it stops over an interval of time. And I'm just going to call that interval of time from A to B. So if I want to know the difference between where I started and where I stopped, I'm just going to integrate the velocity function. What's really important to realize here is, again, that this is not giving me, integrating velocity is not giving me the position, it's just telling me the displacement. How far did I get from where I started? If we want to find position, we actually need to have two pieces of information. The first thing I'm going to need is my initial position, which is really where did I start? So my starting point. And then I'm also going to need the velocity function. Because in order to find position, I need to know where did I start, so I'm just going to call that my initial. And then I'm going to add, well, how far did I get from where I started? And that will give me the position. So I'm going to take my initial position and add how far I got. And that will give me the position. Now, one thing that we'll see as we go through some of these FRQs is that wherever this initial position is, that needs to match the lower bound of my integral. And so we'll get into that a little bit more later. All right, so now we've got displacement and position. For total distance traveled, okay, the idea here is that when we integrate a velocity function, it automatically considers, I think we don't need to worry about this blank, it automatically considers the direction an object is traveling. So if an object goes backwards, it subtracts that value when we integrate. And so that's exactly why integrating velocity gives us this displacement. It takes how far we traveled to the right and subtracted how far we traveled to the left, so we just get that difference. So for total distance traveled, what we really want is all the distance traveled. We want to consider that all as positive, even if we're going backwards. So in other words, for total distance traveled, I don't want to subtract out that area. So what we do here is we're going to integrate the absolute value of that velocity function. Now it takes all of that area under that curve and makes it positive, so then when we add it up, we get the total distance that we traveled over that interval. Okay, last part here then where the speed is increasing versus the speed is decreasing. This doesn't really change, and it actually makes it easier for us having the velocity function because it's one less derivative we have to take. So to determine whether an object's speed is increasing, or in other words, if we're speeding up, or if it's decreasing, so we're slowing down, we need to compare the two values of the velocity and acceleration. So in other words, if v of t and a of t have the same sign, that means I'm speeding up. And on the other hand, if v of t and a of t have different signs, let me move this up so I don't run off the screen. If they have different signs, then I know I'm slowing down. And again, you guys have worked with this before. It showed up in Albert.io, so that is not a new idea. So we're going to go through and do two problems, and then you'll have some time in class to work through a bunch of examples to make sure we've got this down. So here we go. First one, we're going to have a graph of the velocity function. So it says the graph given shows the velocity function. So I'm making sure I know this is velocity. For an object moving along a straight line from time t equals 0 to t equals 8, at t equals 0, the position of the object is 5. So that's what we were talking about, that initial position. All right. So now we've got a couple questions to answer here. The first is, when is the object at rest? And I'm going to make myself a note here. I know an object is at rest when my velocity is equal to 0. Since this is the graph of velocity, I just need to find the zeros here. So that's going to tell me at time equals 5 and time equals 8. So I've got t equals 5 and t equals 8. All right, so in terms of justifying, I would say the object is at rest at t equals 5 and t equals 8 because v of t equals 0 at these values. All right, now moving to the right, I'm just going to make a note here. I know I'm moving to the right when my velocity is greater than or equal to 0. So in this case, my velocity is greater than or equal to 0 when it's above the x-axis. So for those values here, so I would say the object is moving to the right on the interval. I have from 0 to 5 because v of t is greater than or equal to 0. And so then the last part here, obviously, when it's moving left is when my velocity is less than or equal to 0. That's when it's below the x-axis here. So the object is moving left on the interval from 5 to 8 because my velocity is less than or equal to 0. Okay. So now we found out some basic information from that graph. The next thing it's asking us to do is to evaluate the integral from 1 to 6 of v of t dt. So let's take a look. Obviously, we're going to have to break this up. We're going to use geometry here to figure this out, but we're going to kind of have to break this up into a few different intervals. So the first thing I'm going to use here is just my little square. So I've got 1 times 1 plus, it looks like here I'm going to have a trapezoid. That trapezoid's height is 2. So 2 over 2. This height is 1. plus 2. Now I've got a triangle with a base of 2 and a height of 2, so 1/2 times 2 times 2. And then from 6, I'm going to have to subtract this triangle. So I'm going to subtract 1/2. The height, or the base of that, is 1, and the height is 2. So let's see what we've got. We've got 1 plus 3 times 1 is 3. Plus, we get another 2 here, and then minus 1. So we're going to get 5 there, it looks like. Oh, looking at this, I made a mistake here, right? We're integrating. Our starting value is 1, so I don't want to include the area here from 0 to 1. So this should go away, which means this is gone. So what I actually have is 3 plus 2 is 5 minus 1 gives me a value of 4. Okay, so sorry about that. Okay, now it's asking us to explain the meaning of the result. So we need to remember, we said integrating velocity, right, gives us the displacement. So that means the displacement of the object over the interval t equals 0, or excuse me, there's that 0 again, t equals 1 to t equals 6 is 4. And again, in terms of keywords here, they're going to be looking for, did you know it was displacement? Did you give the interval? And then did you give the value? Now, if I knew units, I would include that as well with my displacement. Okay, next is the position of the object at time t equals 5. Well, for position, we said we needed 2 pieces of information. We said we needed the initial position plus the integral. Now, my position, it told me that at time t equals 0, the position of the object is 5. So my integral, since this was at my initial value is time t equals 0, my integral, that lower bound, also has to be 0. So I'm going from 0 to 5 of v of t dt. Right, making sure we're making that connection. My initial value was at time t equals 0, so my lower bound is also t equals 0. So my initial was 5. I'm adding the integral from 0 to 5 of v of t dt. Well, let's see. Now from 0 to 5, I knew that. I'm just going to do this part here. From 0 to 1 is just 1. We already had this trapezoid, right? My height was 2 over 2. Let's see, it's actually this expression here. So that was 3. Then from 3 to 5, the area of that rectangle was 2. So I know that's 6. So my position then is 5 plus 6, which is equal to 11. And again, if they had given us units, we would include them there. All right, so now I've got the position is equal to 11. Now I want the total distance traveled from 0 to 8. So now what we need to remember is that if I want the total distance traveled, I need to take the absolute value of this area, right? So now instead of subtracting it, I'm going to add it. So essentially what we're doing is we're taking the integral from 0 to 5 of v of t dt, and then we're adding the absolute value of the integral from 5 to 8 of v of t dt. So 0 to 5 we just found out was 11, plus, now again, this would normally be negative, but it's because it's below, but we want the absolute value. So essentially we're taking the absolute value. This, we have a trapezoid here. So normally it would have been negative because it's below. The height of that trapezoid is 2 over 2. My base 1 is 1. Base 2 is 3. So I have 11 plus the absolute value of -4. So 11 plus 4 is equal to 15. Okay, again, we wanted that absolute value, so we were adding up that total distance. Okay, last question now for part E. I don't know, let me see if I can get the question and the graph in here. Excuse me while I play around with this a little bit. All right, so it wants to know at time t equals 2, is it speeding up or slowing down? So I know I need to compare the sign of v of 2 and a of 2. Now, for v of 2, that's easy. Since the graph is velocity, I just look at 2, and it's clear to see here that's above the x-axis, so I know that's greater than 0. Now, acceleration at times 2, I know acceleration is just the slope of velocity. So at time 2, if I look at my graph, that has a positive slope, so the sign of that is positive as well. So now I would say the object is speeding up at t equals 2 because v of 2 and a of 2 have the same sign. You could also say that v of 2 is greater than 0 and a of 2 is greater than 0. Again, they're looking, do you know that you have to compare those signs? All right, so that's what this might look like if you're given a graph for velocity. Let's go ahead and flip to the next page. And now we have a function for velocity. Luckily, this is going to be a calculator question, so we'll be able to use that to help us through this problem. So we have our velocity function. It's telling us that at time t equals 0, the particle is at position x equals 1. So there's that initial position. Okay, so this part A says find the acceleration of the particle at time t equals 2. Well, I know the acceleration at times 2 is just the first derivative of velocity evaluated at time 2. So I'm going to use my calculator. I'm going to go ahead and use my Math8 function to find the derivative of velocity and evaluate it at time t equals 2. So I'm taking the derivative with respect to x. I have the opposite of x plus 1 times the sine of x squared divided by 2, and I'm evaluating at 2. Okay, so I have about 1.588. So I'll say 1.588. Okay, so that's the acceleration at time 2. Now, it wants to know, is the speed increasing at time t equals 2. Again, that's where I'm going to need to compare with the sign of velocity. So this answered the first question, but to answer the second question about the speed, I need to calculate my velocity at times 2. I don't know why I keep saying times. At time 2. So I'm going to use my calculator to do that. Let's see, 2 squared is 4 divided by 2 is 2. And that's going to give me a negative 2.728. So now I can see my acceleration was positive, my velocity is negative, so we would say the speed is not increasing at t equals 2 because a of 2 and v of 2 have different signs, so we know we're actually slowing down. Okay. All right, next question here. Find all times t in the open interval from 0 to 3 where the particle changes direction. All right, so we know it changes direction. We're going to look for where v of t equals 0 to start off with. And then we're going to see, does it actually change sign? So does it cross the x-axis? So let's go ahead. We're going to type into our calculator here our velocity function. Let's see. Ooh, and this is messy, so we'll probably have to zoom in a bit here. All right, so I'm going to change my window. I'm probably just going to do -5 to 5 and -5 to 5. So I can get a little better picture of what's going on. I could have gone 0 to 5. All right, so 1, 2, 3. So it looks like I crossed the axis one time in that interval. So I'm going to find that 0. So somewhere below, I'm going to pick a point above, hit enter, and so that happens at 2.507 about. Okay, so we would say the particle changes direction at time t is approximately 2.507 because velocity changes from negative to positive at this value. All right, this has been a long enough video, so I think it'll be worth stopping here. We'll do the next two parts of this example tomorrow in class, as well as covering any questions that you had problems with in the video, and then you guys will get to the practice. So again, thanks for hanging in with a longer video here, and we will see you in class.